Hello and welcome to this lecture on mass transfer. My name is Reinhold Knee and I will look today at fundamental quantities in mass transfer. And for this, we'll consider again this picture that we had in the last video. It shows an enclosed volume which is denoted by capital V. You have two different gases in that volume. The gases are the red dots and the blue dots, and we assume they have constant pressure and temperature. Now let's look at some quantities to describe molar level, mass level, and so on. So this leads me to this table, which looks quite busy, but don't worry, it goes from simple to a bit more complicated, and in most cases things can be put into one another to derive more complicated formulas. So you can derive a lot of stuff. It's just important to know a few ones, and you will familiarize with those while you work through the mass transfer lectures. So let's get started. I'll pick here my laser pointer. The first one is just the mass, the filling mass in that volume. We denote that component-wise M1 or M2, small m, and the unit is kilograms. The molar masses of these gases is basically the weight of 1 mole of these gases. That's with capital M, so capital M1, capital M2, kilogram per kilomole. The partial density is the density of one component, so this is either rho 1 or rho 2, and it's the mass divided by the volume. And again, here the unit, that's kilogram per cubic meter. The mixture density is somehow the average density, so we sum up all components divided by V. So mixture density rho is M1 plus M2 divided by V for our binary mixture. And again, the unit is kilogram per cubic meter. If we go then from density to molar properties, here the molar quantity, like how much of substance in terms of molecules or moles is in. So this is denoted by small n, and this is the mass divided by the molar mass. So we divide kilograms by kilograms per kilomole and end up with a unit of kilomole. And I think the indices are self-explanatory. The molar concentration is the number of molecules or the number of moles divided by volume. It's denoted by capital C, so this is N1 over V or N2 over V. Unit kilomole per cubic meter. The molar concentration of the mixture, as it was the mixture density, we sum up here the number of moles, so N1 and N2 divided by the volume, and we call that capital C, no index. It's kilomole per cubic meter. The mole fraction is then relating the molar quantity of one substance to the sum of all the substances. In our binary mixture, that's just N1 and N2. So psi1, that's the variable used for mole fraction, is N1 divided by N1 and N2. Psi2 is N2 divided by N1 plus N2. And both can be also expressed by C partial molar concentration divided by the molar concentration of the mixture. This is dimensionless. Mass fraction is the mass of one substance divided by the total mass. It's denoted by Xi. So Xi1 is M1 divided by M total. Xi2 is M2 divided by M total. And here this can also be expressed as partial density over mixture density. And again, this is a non-dimensional property. The partial pressure is the pressure that is exerted by one component in this volume. And this is denoted as P1, and it's then derived from the universal gas constant divided by molar mass times partial density times temperature. So we can also put in here the molar concentration if you'd like to express it that way. And the same holds for component 2. Unit Newton per meter squared, and please put in the properties, check for the units, and look if the unit for pressure here really comes out. With that, let's move on to derive some relationships between mass and molar fractions. We'll start with the definition of mole fraction. So psi1 is n1 over n1 plus n2, or c1 over c. Now let's have a look at c, and let's have a look at what n can be expressed by. So if we express n by the mass divided by molar mass, we can here put in for m1, that's partial density times volume. If we look at c and xi, c1 is n1 over volume, and xi is m1 over total mass, or ρ1 over ρ, partial density over mixture density. Now we can put this one into the other. So replacing n1 by the expression up here leads to what we see here, and then we get for c1 that's ρ1 over m1. And this leads us to the expression for the mole fraction in terms of mass fraction. So see this is here c1, and this is c1 plus c2 when you look up here. Now we multiply that with 1 over mixture density, and by this then end up with mass fraction over molar mass for component 1, and here we have that for both components. Now we have related mole fraction to mass fraction, and this might be a quite helpful relationship for some of the calculations you might do in the future. The mean molar mass is just the sum of the masses divided by the sum of the molar quantity. We extend that by 1 over V, and then can express this as mixture density divided by mixture concentration. Now with that, let's move on to pressure. For pressure, we have one important law which is called Dalton's law, and that's total pressure is the sum of the partial pressures. And you may use here as a bridge if you don't remember this, but I assume you have seen this in your studies earlier on and you know the relationship. Well, I took here a picture from a Lucky Luke comic. There were 4 brothers called the Daltons that were always seen together. And if we say this is components of air, we could say the tallest one, that's N2. Then we have oxygen, CO2 and rare gases. And oxygen will be in the air that we exhale, be more prominent than rare gases. When we look at the air that we take in, then there is more rare gas in than CO2. Now with that, let's have a closer look if we how to transform that and get, for example, to mole fraction. So if I divide here by total pressure, I get the 1 on the other side and these ratios on the other side of the equation. If we get further, then this is C1 over C plus C2 over C, or psi1 plus psi2. This means I have a direct relationship between psi and partial pressure. If we look at that, what this means physically, I can interpret pressure as basically how much the molecules in the volume hit or push at that wall. And I think it's pretty evident that when I increase the number of molecules, I will have more pushing or more pressure inside. So I can then relate here my molar fraction that tells me how much of the substance is in as the partial pressure divided by total pressure. This might be a very useful relationship for you if you need to determine psi, and can get, for example, for steam, partial pressure from steam tables, and so on. With that, let's